Okay, everybody, today we were talking about exponential equations or exponential functions. So if the exponent is the variable, or x, it's going to be an exponential equation. Okay, so we started off with a topic, and I said, okay, what if you start with 1 penny, and you double that every day for 31 days, right? So it goes from 1 penny to 2 pennies to 4 to 8 to 16 to 32 pennies, right? 64. Well, how much money would you have at the end of 31 days? So we looked at the problem. So first what we did, we started off with having to graph it. Okay, so then I started off with, with 0.1 times 2, because we're doubling it, times that by 2, times that by 2, and so I'm going to get about 8 cents, and then times that by 2, and I get about 16 cents, times that by 2, I get 32 cents, times that by 2, I got 64 cents, times that by 2, and then I got $1.28, times that by 2, and I got about $2.56. So I just did a graph. I times that by 2, so I'm doubling, $5.12, and times that by 2, and I'm up to $10. So over 10 days, I'm up to $10. Okay, so all right, so then I graphed it, and it starts to get steep here because it's an exponential, and this is what exponential equations do. They start to get steeper and steeper and steeper. They start to grow super fast. One of the things we also talked about, the fact that it will never equal 0, because if you take half of a half, half of a half of a half, you keep taking half of something, it will never equal 0. So we put this invisible imaginary line here called an asymptote. This imaginary line called an asymptote is like a borderline, it's a boundary line. Say, okay, it's going to come down, but it's never going to reach 0. It never reaches 0, so it gets closer and closer to 0, but never gets it. So the asymptote, the horizontal asymptote, is a borderline, okay? We know it's exponential growth because it's growing. So the equation we wanted to use was y equals 0.01 for 1 penny times 2 to the x power. Now, if I want the 31st day, right, I'm just going to use my calculator. So I'm going to plug in 31, and I'm going to find out how much money. Any guesses? Well, a lot of kids guess like $1,000. Somebody guessed $2 million. That seemed like a lot, but let's find out what it really says. Now, this is in terms of dollars, 0.01 times 2 to the 31. Oh my, it's $21 million. So by the end of the 31st day, this is 21 million. We started with just 1 penny. 1 penny doubled $21,478,836.48. Okay? Wow. That's exponential growth. Things got big fast. Okay, then I did a second example talking about exponential decay. So we start with a problem I made up. It's all pretend, but a scientist starts with 800 grams of a radioactive substance. This substance will decay at a rate of 15% per year, so it's going to get smaller. So you're going to take 800. So I said, okay, we'll take our 800, clear this, and we'll multiply it times 0.85, because that's less than 15%. Goes to 680, okay? So then I multiply that times 0.85, because that's less than 15%, 580. Multiply that times 0.85, 491. I multiplied that times 0.85, and I got 471, and I kept multiplying by 0.85, and I got smaller and smaller and smaller. So I drew in a graph, starting at 800, and it slowly went down. Now, we also talked about the fact that it will never be 0. Keeps getting smaller and smaller and smaller, but it will never equal 0. Okay, now, why 0.85? Well, the equation we want to use is this one. If we've got a percentage of growth or decay, we're going to use the y equals a, which is the beginning amount, which is 800, parentheses 1 plus or minus r. Now, r is the rate, plus or minus because it's either growth or decay. Now, we had minus because it's definitely a decay, so it's getting smaller. So what we have is this equation. So I want 800, because that's my beginning amount, times 1 minus 0.15. 15% is 0.15. And of course, 1 minus 0.15 is 85. Think about it this way. You go to the store, you have 15% off, so you don't have to pay the 15, but you got to pay the 85, okay? Anyway, that's our equation. And so then we have a graph of it. Then we finally say, okay, how much is left after 50 years? So I put 50 in for t, and I used my equation. So 50, I want 100, 0.85 to the 50 power because 1 minus 0.25. So then I went and used my calculator, went 800 times 0.85 to the 50th year, and boy, it's almost all the way gone, down to about 0.236 grams. It's slowly disappearing. Okay, that's all I have on growth and decay. If you have any questions, come see me.